you have learned that the transport phenomena of electrons in metals is studied by a very basic equation which is called Boltzmann transport equation. And already in the previous lecture we have discussed this Boltzmann transport equation. Okay. Now actually we will see the applications of this Boltzmann transport equation. And in this regard we will discuss two problems. First one will be the electrical conductivity of metals, and the second one will be its thermal conductivity. Okay. Actually these are also called Sommerfeld theory of thermal conductivity and Sommerfeld theory of electrical conductivity. Okay. In fact, when you say Sommerfeld theory of electrical conductivity, you mean that this is theory of electrical conduction on the basis of Boltzmann transport equation and Fermi-Dirac statistics. Okay. You have learnt already about this electrical conductivity of metals earlier in my lecture, but that was actually classical theory or Drude-Lorentz theory. But now we are going to see the same problem on the basis of Boltzmann transport equation and using the Fermi-Dirac statistics, that is accepting the quantum behavior of electron. Okay, and this theory was provided by Sommerfeld, so this is also called Sommerfeld theory of electrical conductivity of metals. Okay, you know, if you have to pass an electric current through a specimen of a metal or a conductor, what mechanism you follow? Actually, we simply connect the specimen to a source of voltage. As you can see in this figure, I have considered a specimen here, AB, and a voltage source which establishes a potential difference V between the two ends A and B of this specimen has been applied. And you know, due to this applied voltage or this potential gradient, actually an electric field E is produced inside the metallic specimen. You know, in electrostatic condition, the electric field inside the metal is zero. But when we establish a potential gradient or a potential difference across the specimen, then an electric field is developed. Okay, this is in fact an external electric field, and this field is directed from higher potential to lower potential. So in accordance with this figure, the electric field inside this specimen will be directed from A to B, and I have taken this direction as x direction. So you can also say that I have applied an electric field E along x direction across in this specimen. Okay, and you know all these mechanisms. This electric field will exert the electric force which is equal to minus E times capital E on each free electron, which was in random motion before the application of this field. But after the application of this field, the electron moves under the electric force exerted by the field, and the motion is a systematic motion in against of the electric field because electron has negative charge, and so electric conduction takes place. Now through any section of this metal, a net flow of charge takes place, and so electric current flows. Okay, but in absence of this potential gradient, the motion was random, no net charge was flowing through any section, so the net current was zero. Okay, this is the basic concept which you have already learned earlier. Now if your aim is to deal this problem by Sommerfeld theory or by using the Boltzmann transport equation, you know, in Boltzmann transport equation we have to think about a perturbing field which is applied to the specimen. Here, if your aim is to deal with the problem of electrical conductivity of metals, what will be the perturbing field? What will be the external field which you will apply on this specimen? Certainly that will be electric field. So you have to think that here there is no temperature gradient, okay, no heating, no fall of electromagnetic radiation on the specimen, no magnetic field. Only we take electric field as the perturbing field in this case. So our Boltzmann transport equation will become very simple. Okay. So let us see, that in basic form, Boltzmann transport equation is written like this. We have already studied this equation in my previous video. This df by dt due to collision, this is equal to f dot del pf plus v dot del rf. Can you remember this equation? You have already studied this equation in my previous video. Okay. Here, F is the external perturbing force. Okay. And this del P is the gradient operator in momentum space. Del R is the gradient operator in position space. Okay. V is velocity of the electron and F is the distribution function. Okay. You are aware of this equation, so I will not talk something more about this. Okay. You have also learnt in my previous video that this df by dt due to collision, this is given like this. This is minus f naught over tau, where tau is the relaxation time, which means this is average time or mean time between the two successive collisions of the electron with lattice. This is relaxation time. And when you say f naught, that means this is distribution function in undisturbed state of the metal. When you have not applied any external perturbing force or field, then distribution function is f naught. And when the external perturbing field is applied, then it changes to f. So f is the distribution function under the field and f naught is the distribution function in absence of the field. Okay. So you can write this Boltzmann transport equation by substituting this minus f naught over tau at the place of this rate of change in distribution function with respect to time due to collision. Okay. So you can write the above equation like this. This is minus f naught over tau equal to f dot del pf plus v dot del rf. Okay. Now in our present calculation, there is a certain limitation. We apply the external perturbing field E, or you can say the external perturbing force F here, but we take this external perturbing force field or force very weak. And when this perturbing field or force will be small or very weak, in fact, in that condition, the electron will slightly displace from its equilibrium position. The displacement of the electron will be very small, very slight from its equilibrium position. And in that condition, the second term in RHS, which is V dot del RF, actually this is called second order term due to the presence of the velocity, and this second order term will be neglected. This will be negligibly small. Okay, and so in our calculation we can neglect this second term. In another way, it is also said that this differential equation is solved by linearizing. You have to make the equation linear, then you will try to solve it. And to make the equation linear, we must neglect this non-linear term. Actually, this second order term is a non-linear term. And so, neglecting this non-linear term or second order term, but this fact will be valid only when the perturbing field E or the perturbing force F is very small, and we consider it. So in this particular condition, Boltzmann transport equation becomes very simple, and What will be that? For writing that form of Boltzmann transport equation, you have to simply neglect this term V dot del Rf. So now under this condition, our Boltzmann transport equation becomes like this. This is minus F naught over tau equal to F dot del Pf. Okay. Now let us see the present situation. I have told you and you have seen earlier that in this condition we have applied the electric field on the specimen in x direction, and so this field will have only one rectangular components Ex, that is electric field in x direction. So E can be simply written as Exi. In other words, you can also say that the y and z component of electric field vector Ey and Ez will be 0. Okay. So the force acting on an electron due to this field will be minus E into E, and E is equal to Exi. So this can be written as minus E times Exi. Okay. And you know what is this gradient of F? Gradient of F, from the definition of gradient, you can write it del F by del Pxi plus del F by del Pyj plus del F by del Pzk. Okay. Del P is the gradient operator in momentum space. So at the place of x, y, z, you have to write Px, Py, Pz. Okay. So F has been defined here. Gradient of F is defined here. So now you can see what will be this scalar product, F dot del Pf. You know, when you will take the scalar product of this minus Exi with this, only I dot I will be 1 and I dot j, I dot k will be 0. So your result will be minus E into Ex del F by del Px. Okay. This is very simple calculation. So in present situation, you can write that transport equation in this manner. This will be this much, minus F naught over tau equal to minus E times Ex del F by del Px. Okay. Now here you can see, since this distribution function f is a function of only Px, not of Py and not of Pz. So instead of writing this partial derivative, you can also write ordinary derivative. And so I have written in the next step df by dpx instead of del f by del px. You can write it. Okay. Now think what we have assumed earlier. We have assumed that the perturbing field, the external field, that is the electric field applied on the specimen, is weak. It is not very strong. And in the case of weak field, there will be a very slight change in the distribution function f. And so df by dpx will be almost equal to df naught by dpx. Here f naught is the distribution function in unperturbed state, undisturbed state, and f is the distribution function in perturbed state. But since perturbation is very small, so f and f naught does not differ much. And so for a time being, we can approximately take this df naught by dpx equal to df by dpx. So in the next step, you can see I have taken df naught by dpx instead of this df by dpx. Okay. Have you understand? Definitely you have understand. Okay. Now equation 3 is actually, now you can say this is the Boltzmann transport equation in present situation under our assumption. Okay. And actually this f minus f naught, this is deviation in the value of f. This causes the electrical conductivity. And so our final aim will be actually to find this f minus f naught. Okay. Here this f minus f naught has been expressed in terms of the momentum. But our calculation will be much easier when we will talk in terms of energy of the electron. Since our electron is a free electron, so its energy means kinetic energy. And kinetic energy, you know, is directly related to the momentum. So from the relation between kinetic energy and momentum, we can transform that equation in terms of energy. So if you assume that this epsilon is the kinetic energy of this electron, then epsilon will be equal to px square over 2m. Okay, px square over 2m. And therefore, if you will take the differential, you will have d epsilon equal to 2px dpx over 2m. Now this 2 and this 2 will cancel out, and so this is simply px over m dpx. But you know, px is equal to m vx, and so px over m, this will be simply equal to vx. So instead of this px over m, I have written here vx. Okay, and hence you can see, since d epsilon is equal to vx dpx, so dpx will be equal to d epsilon over vx. Okay, now we will replace this dpx present in this equation number 3 by this d epsilon by vx. Okay, so replace it. Here dpx will be replaced by that value, and after replacing, you can see this equation. Now this equation will become f over f naught over tau equal to E times Vx times Ex times df naught by d epsilon. So this is one of the forms of this Boltzmann transport equation in present situation. Okay. Actually, our aim is to find the electrical conductivity of the metal, and electrical conductivity will be determined by using the Ohm's law. And according to the microscopic form of Ohm's law, J is equal to sigma E. I have not written it in vector. You can write it in vector form. Okay. So if your aim is to find this sigma, which is electrical conductivity, then you must find what will be the value of this current density. Okay, and current density is obtained by using this relation minus NeVd. Here n is the number of electron per unit volume taking in part in conduction, and E is electronic charge, and Vd is the drift velocity. Okay, so think, you have to find sigma, and for that you have to use this form of Ohm's law, and again you can find same J with using the formula minus Ne into Vd. So first of all, we will find the value of current density here using this formula. Okay, and then we will compare that result with Ohm's law, and after comparison you will get the value of sigma. Okay, so for getting the value of J, first of all we must to know about what is the number of free electron per unit volume taking part in conduction. Okay, but this can be found here by using the Fermi-Dirac statistics, because the approach which we will follow in this calculation is quantum mechanical approach. This is Sommerfeld theory. So you must think that electron is a quantum particle. It has a spin half and two spin states plus half and minus half. All these things you have to consider. Okay. So using the idea of Fermi-Dirac statistics step by step, we will be able to find the number of electrons taking part in the conduction. Okay. Definitely you have studied statistical mechanics, the Fermi-Dirac statistics. If you have not studied it till now, I will suggest you go through my videos on Fermi-Dirac statistics in the playlist of statistical mechanics of my channel, and everything will be you will find there well discussed. Okay, so you know that if we are talking in terms of the phase space, okay, then we know in h cube volume, in h is Planck's constant and h cube represents a volume. In h cube volume, the number of quantum states is equal to 1. Okay, so in unit volume, the number of quantum state is 1 over h cube. Okay, so if you consider that d gamma is the volume in phase space, then in this d gamma volume, what will be the number of quantum states? That will be d gamma over h cube. Okay, over h cube. So d gamma over h cube represents the number of quantum states in volume d gamma in phase space. But what is this d gamma? D gamma is the volume in phase space, and this is actually equal to product of the volume in position space and in momentum space. So if V is the volume in position space and d tau is the volume in momentum space, then this d gamma is V into d gamma. Now, if you take this V equal to 1, that is, you are talking about a physical space of unit volume, then this d gamma will be equal to only d tau. Okay, only d tau. So the number of quantum states in unit volume of the physical space will be what? That will be d tau over h cube. But if you consider a volume element in momentum space, and then this d tau will be equal to dpx into dpy into dpz. So when you will divide it by h cube, you will get the number of quantum states. This represents the number of quantum states. But since electron has two spin states, so the total number of electronic quantum states will be just twice of this value. So I have written here, you can see the number of electronic quantum state per unit volume in a volume element dpx, dpy, dpz in momentum space. Mark this, per unit, when you say per unit volume, it means per unit volume in physical space, in geometrical space, where the volume is measured in meter cube. Okay, and volume element in momentum space is dpx, dpy, dpz. Okay, taking a spin of the electron under account, that number of quantum states will be this much. You have to multiply this by factor 2. This is due to the two spin states of the electron. So 2 over h cube times dpx into dpy into dpz. What is this? This is number of electronic quantum states in 1 meter cube of a volume element dpx, dpy, dpz in momentum space. Okay. And according to Pauli's exclusion principle, in one quantum state, only one electron can remain. So this also represents the number of electrons present in those quantum states. Because in case of electron, since electron is fermion and only one fermion can be in a particular quantum state, so in case of this, number of quantum states and number of electron present in those quantum states will be same. If there is some unoccupied state, then the number of electron will be smaller. Okay, number of, let us consider that there are 50 quantum states, but only 40 electrons are available, then 10 quantum states will be unoccupied. In this condition, the number of electron and the number of quantum state will differ. But if there is sufficient number of electron, then every quantum state will contain one electron. And in that condition, the number of quantum state and the number of electrons present in them will be same. Okay. Now, as I was telling you, that it is not necessary that all the possible quantum states are occupied by the electron. It depends on the availability of electron. So if now your aim is to find that how many quantum states are occupied by the electron and how many quantum states are empty, how you can find? Actually, Fermi-Dirac distribution function is the suitable candidate to find this. You know, Fermi-Dirac distribution function, actually it is also called occupation probability. It means it measures the probability of finding an electron in a particular energy state, in a particular quantum state. So, when you will multiply that number of quantum states by the Fermi-Dirac distribution function or occupation probability, then you will get the number of occupied states, and number of occupied electronic states is also equal to number of electrons. Okay. So, if you are talking about the metal when no perturbing field has been applied, okay, no perturbing field, in that condition, the Fermi-Dirac distribution function is f naught of p. In terms of, I am talking about this function in terms of momentum, not in terms of energy. Okay. So this f naught p measures the probability of finding an electron in a momentum state p, and 2 over h cube times dpx, dpy, dpz. This is the measure of total number of quantum states. So when this total number of quantum states will be multiplied by f naught p, that is the occupation probability, then you will get the number of occupied electronic states dn0. And number of occupied electronic states, I am again telling you, will be equal to the number of electrons, because any occupied electronic state will contain only one electron. Okay. So the number of occupied states and the number of electron will be same. I think everything has been clear to you. Okay. You are getting the things or not? Definitely you have got it. But this f naught of p, this is Fermi-Dirac distribution function in terms of momentum when no perturbing field has been applied. Actually, this function is spherically symmetric with respect to p. Okay. And since it is spherically symmetric, so there will be no net flow of charge and it will not contribute to any electric current. Okay. Only when you will apply the disturbing or the perturbing field, external field, and due to which this Fermi-Dirac distribution function f naught p will change, only then there will be a net flow of charge and current will be constituted. Okay. So actually the change or the deviation in the value of this Fermi function is responsible for the electric conduction. Okay. So I have written that current is essentially determined by the deviation f minus f naught caused by the Fermi distribution by the application of electric field. Actually f is the value of this distribution function in presence of the external field. Okay. So in the presence of an external field, electric field Ex along the x direction, this distribution function becomes f of p. Okay. And now what will be the number of occupied quantum states in the same volume in momentum space. But again, we are taking the volume in physical space to be equal to unity. So now the average number of electrons per unit volume in physical space in the volume element dpx, dpy, dpz in momentum space, and this average number of electron, I am telling you several times that this will be simply equal to number of occupied states, okay? And number of occupied states is found simply by multiplying this number of quantum states 2 by h cube dpx, dpy, dpz by the Fermi-Dirac distribution function, which is called occupation probability. So the product of number of quantum states and the occupation probability f of p, this gives the average number of electrons per unit volume in the volume element dpx, dpy, dpz. And in perturbed state, we have considered that this number is dn. Okay, this number is dn. Actually, this dn minus dn0, that will be the effective number of electron per unit volume flowing under the electric field, and that will constitute electric current. Okay, that will constitute. So now if your aim is to find the current density, I have written it Jx because here current is already flowing, will flow in x direction. So current density will have also only one component Jx. So first of all, let us try to find djx. What will be this djx? As I have told you earlier that this is given as minus dn minus dn0. This will give the net number of conduction electron flowing through unit volume, okay, and times E into Vx, okay. But this is the differential value of Jx. So if your now aim is to find what will be the total current density, then you have to integrate this, okay, for the entire specimen. So Jx is given by minus integral of dn minus dn0 into EVx, okay. Now let us substitute the value of dn and dn0 which we have obtained earlier here and here, okay. You can see this 2 over h cube dpx, dpy, dpz are common factors, okay. And only difference is in this function. Here is f of p and here is f naught of p, okay. So now there are three variables px, py, pz. So I have used the symbol of triple integral. So you can write, after substituting the value of dn and dn0, jx equal to minus 2e over h cube triple integral Vx times f minus f naught dpx, dpy, dpz, okay. But you can see we have already obtained in this equation 4 what is this f minus f naught over tau. So using this equation 4, now we will obtain the value of deviation of the distribution function, that is the value of this f minus f naught. And you have seen in equation 4 that this f minus f naught is given like this. This is E Vx Ex times tau times df naught by d epsilon, okay. So now use this value of f minus f naught here, and then Jx will be given by minus 2e square over h cube times Ex triple integral Vx square tau df naught by d epsilon dpx, dpy, dpz, okay. Now our aim is actually to evaluate this triple integral, okay. Actually this triple integral or this volume integral can be converted into a single integral, okay. And after converting it into a single integral, it will be easier to evaluate it. So let us try to convert this volume integral or triple integral into a single integral. And for this, you can see that Vx square plus Vy square plus Vz square is equal to V square. You know it, okay? But here, X, Y and Z, all the three directions are equivalent to one another. In present situation, I have assumed that electron is drifting on x-axis, okay? Because we have applied the electric field vector on x-axis, so electron drifts in negative x direction with velocity v. But if you will apply the electric field in y direction, the drifting of electron will take place on y direction with velocity vy, okay? And if you will apply the electric field in z direction, then drifting will be on z axis with velocity vz. So all these vx, vy and vz are equivalent to one another, okay? That will be same. And so instead of this vy square and vz square, we can write vx square. So this will be 3vx square, and that will be equal to v square. And so vx square is equal to v square over 3. Okay. So now in our calculation, instead of this vx square, we will write v square over 3. Okay. Now again see, this volume element dpx, dpy, dpz in momentum space can be expressed in terms of only one variable p. You know what is this dpx, dpy, dpz? This elementary volume in momentum space is nothing. It is simply the volume enclosed between two concentric spheres of radii p and p plus dp in momentum space. You can see I have assumed here two spheres. The radius of the inner sphere is p and that of the outer sphere is p plus dp. So the volume of this shaded region is equal to this dpx, dpy, dpz. Okay, this sphere is in volume, in momentum space, not in physical space. So radius is equal to p, and you know the radius of this shaded region will be the volume of this shaded region will be what? That will be 4 pi p squared dp. This is simply the differential of 4 by 3 pi p cube, and this differential will be 4 pi p square dp. Okay, so instead of this dpx, dpy, dpz in our calculation, we can write this 4 pi p square dp. So replace this dpx, dpy, dpz in this equation 5 by 4 pi p square dp, and after replacing it you will get that jx is equal to this much. This is minus 2e square over h cube ex integral 0 to infinity v square over 3 tau df naught by d epsilon 4 pi p square dp. Here the limits for the speed of electron or the magnitude of momentum has been taken 0 to infinity. This is classical idea, because you know in Fermi-Dirac statistics we use the mixed concept. In one hand, when you are talking pure quantum mechanical idea of a spin of electron, but on the other hand you talk about the phase space, which is a purely classical idea. So this is a mixed idea. Here the minimum value of electron is taken 0 and the maximum value of the speed of electron is taken infinity. This is a classical idea. Okay, so the limits for this has been taken 0 and infinity. But in our equation there are two types of variable. One is v and another is p. So we must express this result in terms of only one variable. Okay. Now you know epsilon, which represents the kinetic energy of the electron, that is equal to p square over 2m. And so this d epsilon will be 2p dp over 2m. This 2 and this 2 will be cancelled out, and so p dp is equal to m d epsilon. Okay, and again this epsilon is equal to half mv square, because this is kinetic energy, non-relativistic kinetic energy, and so v square is equal to this much. So in using these, we can express the integrand here in terms of only one variable epsilon. Okay, only one variable, and classically the energy of electron will also have minimum value 0 and maximum value infinity. So the limits will remain same. You can check it from here, that when p is 0, then epsilon will be 0, and when p is infinity, epsilon will be infinity. So the limits remain same. Okay, so after substituting these, the expression for Jx will now like this. This is minus 2e square over 3h cube times Ex integral 0 to infinity 2 epsilon over m. Instead of v square, here it has been written that 2 epsilon over m. Okay, and this factor 3 has been written in outside, you can see, times tau, and this is at each, and 4 pi p, 4 pi, and instead of p I have written a square root of 2m epsilon, and p dp. For p dp we will write m d epsilon. Okay, so after simplification, your result will be Jx is equal to minus 16 pi e square, a square root of 2m over 3h cube Ex integral 0 to infinity epsilon to the power 3 by 2 times tau df naught by d epsilon d epsilon. You can also write it df naught by d epsilon d epsilon. Okay, now actually for evaluating this integral, we think about only those electrons which are in the energy levels near the Fermi level. Let us see that this is a Fermi level. Okay, then you have to think about only those electrons whose energy level is very close to this Fermi level. Only we are thinking about those electrons. It means we are talking about only those electrons which has energy almost equal to the Fermi energy. So in that very condition, the energy will have a particular value, and that will be equal to EF. Okay, and so for those electrons, this factor epsilon to the power 3 by 2 into tau can be replaced by EF to the power 3 by 2 times tau f. Here tau f is actually the relaxation time for electrons with energy almost equal to EF. It means this is the relaxation time for those electrons whose energy levels lie very close to the Fermi level, and this will have a constant value. Okay, so using this idea, this epsilon to the power 3 by 2 times tau can be replaced by this, and that will be a constant, so that will be outside of the integral. And we also know from the property of FD distribution function that the integral of del f naught by del epsilon d epsilon from 0 to infinity, that is equal to minus 1. Here the property of Fermi distribution function has been used. So now use these two facts in equation 6. Now this tau will be replaced by tau f, which will be a constant, and that will be outside of the integral. Okay, and epsilon to the power 3 by 2 will be replaced by EF to the power 3 by 2, and that is also a constant. So the remaining factor will be only the integral of this df naught by d epsilon from 0 to infinity, which is equal to minus 1. So making these substitutions in equation 6, our result for Jx will now become like this. This value of integral which is -1, that minus will make here minus sign plus. And so Jx is equal to 16 pi e square times square root of 2m over 3h cube times ef to the power 3 by 2 times tau f times Ex. Okay. Now, you know that this Ef is Fermi energy, and you have already studied the expression for this Fermi energy in 3D crystal. And you know Ef is given like this. This is h square over 2m times 3n over 8 pi whole to the power 2 by 3. Okay. Here n, you know, this is number of free electrons per unit volume. Okay. So now let us substitute this expression for Ef in our result here. Okay. So Jx will be what? This will be 16 pi e square root over 2m over 3h cube times Ef to the power 3 by 2. Raise power 3 by 2 on this. When you will raise power 3 by 2 on this, what will happen? Actually, in that condition, the power on 3n by 8 pi will cancel out, and here h squared to the power 3 by 2, that will become h cube, and 2m will have power 3 by 2. Okay. So in this way, you can simplify it, that this is equal to this much. Okay. So substituting this value of Ef, our result is like this. Okay. Now simplify it. You can see this h cube and this h cube will cancel out. This 3 and 3 will also cancel out. Okay. And 2m to the power half, and here there is 2m to the power 3 by 2. Oh, 2m to the power 3 by 2. So half power will cancel out, and in denominator there will be 2m. Okay. And this 8 pi will also cancel. This will be in fact 2 here. Okay. So finally you will get that this Jx is equal to Ne square tau f over m times Ex. Okay. So in this way we have calculated the current density. But as I have told you earlier, that the microscopic form of Ohm's law says that Jx is equal to sigma times Ex, where sigma is electrical conductivity. You know what is this sigma? Sigma is electrical conductivity, and our aim is to find this electrical conductivity. Okay, this electrical conductivity, our aim is to find. So by Ohm's law, we write Jx equal to sigma Ex, but our result says Jx equal to this much. So definitely, when you will compare equations 7 and 8, then you will find that this sigma, which is electrical conductivity of our metal, that is equal to Ne square tau f over m. Okay. This result is very significant in due to one fact. When we have applied the Drude model, then we have not talked about Fermi level because Fermi level is a quantum mechanical concept. And in that equation, you have seen that sigma was obtained Ne square over tau, Ne square tau over m. In some of the books, you will also find that here there is factor 2, although that is not very correct, that is not very appropriate. But instead of tau f in that calculation, in classical calculation, in Lorentz-Drude theory, we have tau. But here there is tau f. And what is difference between tau and Tf? Tau f? Tau f is the relaxation time for those electrons whose energy lies near about the Fermi level. Okay. But can you say that since in this equation the
relaxation time has been taken for the electrons whose energy is near about Fermi level, then only the electrons near the Fermi level will contribute to current. Answer is no. Electric current here is contributed by all free electrons. But when we calculate the conductivity, then we should take the relaxation time only for the electrons which is near about Fermi level. Okay? But why? Why? How you can explain this fact? So this is actually a very interesting fact that you can say that it is an interesting. It is very interesting to note that although all electrons take part in the conduction mechanism, but the relaxation times of only those electrons with energy states close to Fermi level are significant in respect of conductivity. You can say. This becomes clear if one looks at this figure. You can see. In fact, in this figure you can see the sphere denoted by the full circle, that is the sphere A. Okay. Represent, that is had been represented by circle, but that is a sphere. Okay. So the sphere denoted by the full circle or the sphere A represents the Fermi distribution in the absence of electric field. That is, this is the Fermi distribution when E is equal to 0. Okay. But when electric field is applied, or you can say in the presence of an electric field along the x-axis, the velocity of all electrons gets shifted by an amount delta V. You can see this is the shift in velocity which I have assumed delta V. Actually, this has been shown by the this dashed circle or the circle B in this figure. So from this figure, it is evident that the distribution is changed only in the vicinity of the Fermi level. You can see here this distribution has been changed significantly, but here there is no significant change in distribution, and that's why in the expression for sigma, instead of tau, we have to take tau f, but it does not mean that in the expression of sigma tau f is present. That does not refer that only electrons with energy almost equal to Fermi energy take part in conduction. But actually fact is what? Fact is all electrons take part in conduction. But whenever you will have to calculate the electrical conductivity, then you must take relaxation time for only those electrons which are near about the Fermi level. Okay. So in this way we have discussed the Sommerfeld theory of thermal conductivity using the Fermi-Dirac statistics and idea of distribution function. And I think this session was interesting to you. So if you find it helpful for you, you must watch it seriously, write down these things in your notebook. Definitely that will be very helpful to you. Thank you very much.